One of the benefits with spectroscopy is making the invisible visible. And we can do that by looking beyond the visible range and leveraging devices like near-infrared spectroscopy, which allows us to see things that aren't visible by the human eye. So let me show you an example of what we're going to do in our quick experiment as we begin getting more to looking at the intersection of measurement science and data science. So I've got 9 squares starting from here, 1, 2, 3 in the top row, 3 in the middle, and 3 on the bottom. And the idea is to go around with our near IR and look for which square has a defect. Now, if we have a defect here that I'm showing you with this black circle, it's pretty obvious visibly where this defect is occurring, and we would expect this particular sample to have a different chemical signature based on whatever detector we're using. Now, however, imagine we have this case here where I have those same 9 squares, but it's very difficult to understand where this defect is because now that defect is invisible to the human eye. And this is where a device like this will come in handy, where we can use this to effectively monitor the process. So in the software, I have set up a method development experiment as I begin looking at how we can build into looking at household products like plastic containers, cosmetics, and many other things. And so I'm going to begin showing you how we can develop methods for the various product forms that we're going to be analyzing. And I intend to bring you on that journey, but I want to motivate you with what we are going to do on this little experiment here. So what I'm going to do is take a sample every 6 seconds, and it will start after 10 seconds. And we're going to just move the near-infrared spectrometer through each of these squares, and we will look at the spectrum that's produced, looking for which spectrum looks different than the 8 others. There should be at least one sample that looks different than the others. And so we're going to take a look at that together and determine where it is. So I want you to tell me now in the comments which square you think will be the outlier. 1, 2, 3, 4, 5, 6, 7, 8, or 9. Let me know and we'll begin testing. And so I'll begin the first square, and every time this flashes, I'll move it to the next location. It starts after about 10 seconds. And so I've got to keep an eye on when to move it and tracking the data. So I'll switch back and forth between the cams and let you see what's going on. So far they look pretty consistent. And we're just going to continue moving until we see which sample looks kind of wonky. I'm now on square 6. And so far they look really consistent. I am now on square 8 or 7. Now I'm moving to 8. Oh, it looks like we did have one pop up. I think that was square 7. That looks really wonky. And so that's all of them. I'm going to stop the experiment. And if I look at the data line, it looks like it was this square. So that would be square 1, 2, 3, 4, 5, 6, 7. So if you thought square 7, that was great. And one of these squares actually had a glue stick. So it's invisible to the human eye. If I, again, show you where we are on this paper, that was this location here. And that's the benefit of using near-infrared spectroscopy, using a device that allows us to see in the visible realm that even when putting that on the main camera, it is virtually impossible. So that is the benefit. That's what we're going to do when we look at different plastics, different cosmetics. But I want to give you a primer with what was possible with this type of analysis, even for a simple experiment like this. I'll do more of these in the future just so you can see what's possible, maybe even setting up some red herrings where we see what's invisible even to near IR. In any case, I'll see you in the next video. Peace.